Hey guys, so we're gonna get started. So previous lecture, guys, we went over the dot product and the matrix multiplication and mapping data from one vector space to another vector space, right? And that essentially is a neural network. Make sure you understand that topic really well if you still haven't, because it's like the fundamental thing that is happening throughout. All right. Now I'm going to kind of continue to do that, but in the context, more in the context of an LLM. So you may have heard that LLMs are use a mechanism called the attention mechanism. So that's what we're going to talk about right now. What is attention? And sometimes when people describe attention, they'll throw like, oh, there's keys, queries, and values. And these key queries and values do this and that. But the way that we're going to look at it is as matrix multiplications, right? Because there's no mysticism there, no magic. You will see the operations as they are. And then again, I'm just using random data because I'm only building the architecture, but we're not training it yet. Training will provide the weights, okay? But we're going to talk about attention. What attention is, keep in mind here, it's in the context of a large language model, so we're looking at text. So I'm going to give you one example of what attention kind of is. So, I have a sentence. The robbers went to the bank and stole the money, right? Versus, the couple was walking on the bank of the river. Do you see that? In both sentences, I use the word bank. Do you guys see that? Which is spelled the same, bank, right? But one is in the context of what? Of financial institutions and buildings. The other one is in the context of a river, like a sandy area next to water of a river. Do you guys see that? So keep that in mind because this whole discussion is about that sentence, right? And what the attention mechanism does. Okay? All right. So LLMs under the hood, understanding attention in transformers. So, this repo walks through the attention mechanism, which is at the core of transformer models like GPTs, BERTs, Llama, and it's implemented from scratch in PyTorch. The objective is to implement and visualize how queries, keys, and values are derived from token embeddings, how dot product attention is computed, and then later next week we'll talk about masking. I'm going to skip that for now because that's probably the hardest part of this whole thing. Okay, so what I'm going to do is, basically say that in attention, right, you have a matrix, which is the original input matrix, and then you're going to create three more matrices called Q, K, and V. But these three matrices are created from X. So you'll see that here. So the operations are going to be like this. Notice that all three of these use X as the input. Remember, what is the at sign? It's the matrix multiplication. So you're essentially taking X, matrix multiplied with a weight matrix, and adding a bias over here, and you transform X into Q, you transform X into K, and you transform X into V. Do you see that? It's the same operation we've been using before. Why we're doing this, let's get to the end and then we can talk about it. But initially, let's just understand that mechanically, what's happening is I'm taking X and I'm doing a matrix multiplication with its corresponding weights matrix. Let's ignore the bias for now, just to keep it simpler. Okay, so that's the idea. So what's going to happen is, if you notice, once I've created those three matrices, I'm going to perform yet another matrix multiplication, but this time between Q and K. Do you see that? You can ignore this. This is just like for the aligning things properly, but essentially Q, matrix multiplication, K. So essentially, it's the same as saying, a matrix where you have on the rows and on the columns the same sentence. So the robbers went to the bank and stole the money. The robbers went to the bank and stole the money. Why do you do that? So that you can compare all these words to all these words. Do you see that? That's essentially what I'm doing. So the robbers went to the bank and stole the money. Bank. The robbers went to the bank and stole the money, but now I can compare this word bank to all the same words in that sentence. And what's important is bank and rob the money are important to understand that I mean bank in the context of a financial institution. Do you guys see that? That's essentially what attention is. You pay attention to the word robber to figure out the meaning of the word bank. If I was talking about the couple was walking on the bank of the river, the couple was walking on the bank of the river, bank, river. The correlation between those two is high, and then the meaning of bank is different from in the previous example. Do you guys get that idea? So this is what attention is trying to do. It is trying to compare the words in the sentence and see which ones are very important to understanding the meaning of the other ones, right? And in this case, the word that needs disambiguation, of course, is bank, because it's a word that can have different meanings. All right. So that's what we're doing. But notice that instead of in this matrix multiplication, we don't really do X matrix multiplication X. We do Q matrix multiplication K. So before we do that comparison, the X's are transformed by a set of weight matrix, by a set of weights. And that you can think of it as just giving it one extra layer to kind of process this a little bit. You see that? That's kind of the intuition that you should think about, because that's really what's happening is you're not comparing X directly. You're comparing X after you multiply it times a set of weights. So you did transform it a little bit. So instead of it, another way of saying it is, instead of comparing it in the real space, you kind of compared it in a more latent space, right? You gave it a little bit more room when you did the comparison. So going to the intuition of 4 versus 6, right? So going into that intuition, let's try that. And this is like it's like in this, I think you'll get the whole idea. So think about this. So iris, again, it's not a language, but we understand iris, right? So there's 1, 2, 3, 4. So what is it? Sepal length, sepal width, petal length, petal width. So in the context of attention, you would be comparing petal length, petal width, sepal length, sepal width to petal length, petal width, sepal length, sepal width, right? But instead of that, we create Q and K, which is an analogy similar to when we have 4 and we converted it to 6. Do you see that? So now the attention that we use is not at the real space of petal length, petal width, but at a transformed latent space. And that just because that way it has a little bit more room. So whereas this is 4 and 4, the actual comparison would be between 6 and 6. Do you guys get that? So this is essentially where we're doing the comparison. But that 6 is based on the original 4. It's just that we did X and X and transformed it with the matrix multiplication, and they had their corresponding set of weights, Q, K, that they had to learn. So that's essentially what the way that you can see it. We're not actually looking at it as petal length, petal width, but we're looking at it as a transformed version of that. All right. So that's where the K and Q comes in. And then the V is just actually a mechanical thing that comes later. All right. So any questions on this idea? Does this make sense? Yeah, go ahead. Say that again. Mm-hmm. Yes. True. Hmm. Sure. Okay. I see what you're saying. So it's like, yeah, I get your point. So it's like I said this, and then I made it, but it's, I guess, more like, and I got one that was six over here and one that was six over here, and then I multiplied these two. Yeah, you can think of it that way. So you're right. It's a little bit more than that. Yeah, go ahead. The shape is going to be, yeah, the shape of it is going to be for, n by n. It actually becomes a square matrix, and we'll see that in a second. Because actually it makes sense, right? So it's the sentence compared to itself, so it should be the same size in both dimensions. Okay, so again, this, we're getting ahead of ourselves because that's kind of the intuition, but let's take a look at the operations themselves. Okay, so let's go back. All right, so go here. So again, in attention, we start with some data. This is going to be our data. Okay, and then we're going to we're going to transform that data into Q, K, and V. Once we have Q and K, we're going to matrix multiply them to produce something that is squared like this. And then that is the attention mechanism itself. From there, we're going to do another operation with V. Okay? So now let's try this out. So this should be this Jupyter notebook I have here. Should be this one, attention, linear algebra attention. So we're going to go through it. Okay, so this is the whole sample. So I'm going to continue with Colab here. All right, so I'm going to need maybe, I'm going to use Torch here, make sure I have all the libraries. Okay. I'm going to create X first. So this is going to be X. So here, this is going to be a tensor of size 32, 40, 5, 12, which might seem pretty difficult to understand, but really 32 just means 32 examples. It's the batch size. So think of it as having 32 sentences in there. Do you see that? 40 is the length of the sentence. We're going to keep it simple and assume every token here is a word, right? Although in reality, it's more like a syllable, but let's assume 40 is the length of the sentence. So I have a batch of 32 different sentences, unrelated. Each sentence is size 40. And then I have this weird 512 in there. Do you guys see that? So what does that mean? So let's go back to the whiteboard. Okay. So I have X. It's a cube, right? Like a hyperdimensional cube of dimension 32, 40, 512. Let's simplify that. Let's ignore that 512, and then it should make more sense. It's just a two-dimensional thing of 32, 40. Do you guys see that? Each of these is a sentence. So we can just look at one of size 40. What is in there? The people were on the bank of the river. That is essentially what these 40 things are, right? So the, comma, I'm just going to use like the first letter to keep it simple, or a few letters. So people, comma, were on, dot, 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 bank, 40 of them. Do you guys see that? That's it. That's what the 40 are. Now, the key thing is neural networks don't take strings, right? So instead, each one of these words has to be a number. So we create this thing called the vocabulary. So before you get to the LLM, there's a first step. And the first step is just identifying the vocabulary that you're going to use. Believe it or not, GPTs like GPT-3, etc., use some vocabulary of around 50,000 tokens. That's it, about 50,000 tokens. As I said, these are, for our purposes right now, I'm just going to use words. Just keep in mind that they use something like syllables. So they'll use like TA. So for instance, happy, you have hap, but that could be happier, happiest, happily, right? So you break it up into like syllables so you can form other words, right, and be efficient. But for now, let's just say, there's about 50,000 words. So then you create a vocabulary and you map each one of these strings to an integer, right? So for instance, people could be 17. Bank, let's say it's like 56. Die is 3. Were is like 8. River is 5,000 for some reason. Do you see that? So every one of these is just an integer, okay? All right. So my vector now looks like what did I say that was? 3. People is 17. Were is 8. Let's say on is 11. Dot, 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 and bank was 56. Do you guys see that? So every sentence of size 40 is just a list of integers that are coming from some vocabulary that I've created. And there's an algorithm for this called BPE. That's not what we're going to cover right now. Just assume this works. Okay? Give it all the text because it produces a vocabulary. 50,000 words, and each one, or subwords, and each one has an integer. Everyone with me so far? All right. So now we've established that. So I'm going to go over here. I'm going to add my batch size again, which was 32, 40. And then all of these are numbers, 2, 7, whatever it was. And this is what you would feed to the neural network. But those numbers aren't really as helpful, right? Instead, what we need is to represent each of these integers as an embedding. Okay, once again, guess what? We're going back to vector spaces yet again. So, vector space is the thing we've been talking about a lot. Now we create another vector space. This vector space is what? Is a matrix, yet again. How many rows in this case? 50,000. Why 50,000? Because every one of those words, those 50,000 words in the vocabulary that goes from 1 to all the way to 50,000 will have a new representation. So for instance, I take the word 17, which was, cat, let's say. The word cat is ID 17. Well, actually, it's going to be a vector of size, whatever I want this to be honest. But I think in the original paper, this was 512. This is a vector space. So this is R512. Do you see that? Make sense? Why would you do this? Because you have 50,000 words and you're going to use 512 columns to represent them. So for instance, think of it this way, cats and dogs. And dog is 53. Maybe in here, there's a column 100, and it represents things that have 4 legs for whatever reason. So how do you think that they're going to, in this space, this one and this one are going to have a value that's high maybe for things that have four legs. And then I have the word, let's say index one is Paris. I don't think Paris has four legs, right? So then what would you expect the value for column 100 to be? Very low, right? So if we were saying that this was high for having four legs, then Paris would have a very, so let's say this is 1,000, this is 1,000, this one over here would be like 3. You see that? So it captures how many legs it has about that word. But obviously human, we don't set that up. We let the neural network figure it out. Now, Paris is a city. So there might be a column 50 in there that captures something about a place where millions of people live, right? And so then this column, 50 for Paris will be 2,000. Do you guys see that? And then imagine down here, there's the word 1,000, and that's Washington, D.C. So guess what? Does Washington, D.C. have a lot of legs? Probably not, right? So this value is like a 2. But does it have millions of people living there? Probably. Maybe less than Paris. I don't know. So let's say it's 1,500. Do you guys see that? So the embedding space captures something about each word as it's going into the neural network. And this is done in the neural network itself. So actually, every word gets converted from a string to an integer and then to a vector of 512. So that's why the matrix that was like this, where it had a 56 and a 60, now imagine it's actually, that 2 is a vector of 512 in there, right? And then the 7 is a vector of 512. And then the 56 is a vector of 512. Do you all see that? So you need that third dimension, right? So it's like, X and Y, but then 512 coming out this way. And so that's why our tensor, now if we go over here, that's why our tensor then now it should make sense. 32 sentences, all of length 40. If we just had the IDs, this is all we need. But because every single one of them is actually a vector of 512, we need the additional in the third dimension. Make sense? And so this is exciting. Yeah, go ahead. It's the fixed size that you chose. So I use pretty much all my numbers are based on the original attention paper of 2017. This now can be bigger. So the limit, it was 512 because back then they had only, I think the initial 2017 paper used 8 GPUs. But now they can use thousands and they have A100s and whatever. So this can be much bigger. Yes, sir. Yeah, it can be any number as long as you have enough GPUs and you need it. Like if somehow increasing that makes the GPT more intelligent, you do it. It's faster, yeah. So it'll run with fewer GPUs, less RAM requirements, things like that. Mhm. That's right. Yeah, an easier example, your homework assignment, right? So you're going to use this LLM and you're going to train it and it's taking you all weekend to run and you're not getting any results. You have to make some drastic decisions. And one of the drastic decisions might say, 512 is just not working for me. So I'm going to go down to 256 and see if I can get some result. Because what's the point of running 512 if you never get a result because it's taking too long? So you have to go down somewhere. So actually, you will see in a few minutes or during the next few weeks that some of the decisions in the original transformer are just about performance, about we just don't have enough memory, so how do we do this efficiently? Got it? All right, so that's what. Any other questions? So that's what 32, 40, 512 is. This tensor is the fundamental tensor to understand. Because what's really nice about transformers were actually pretty hard, even for them to fathom, right? So what they built is they built an architecture of one block. A lot of transformations are happening in there, a lot of things. But this is a key thing. 3240, 512 goes in. 32, 40, 512 comes out. Do you see that? So that was key, because then they could do another block where 3240, 512 goes in and 32, 40, 512 comes out. It's just transformed into something else. Right? So essentially that same tensor goes in and out a lot of the layers of the neural network. Okay? And we will later dig deep into the exact thing that's happening, but for now, we want to understand this. Okay? All right. So now, remember that when, I have 32 batches, but we're just going to think of one. Okay, one batch that we have there. So 14512 to do the operations. All right, so let's go back now. So you guys understand, right? I have 32 sentences of length 40, and each word is actually a vector of 512. Okay? So I want to compare these words with each other with the attention layer. So I'm going to go back to here. All right, so now you guys know this is the data. So in the attention mechanism, you would want to compare X with itself, but I just said that we do one transformation before we do the comparison. And that's just a matrix multiplication. So here I'm going to do, I do the first one, Q. So I'm going to grab this. So you can see what I was doing before, right? Don't worry, I'm only going to do this a couple more times and then it'll become easier. But I do want to drill this down into your head, what's actually happening under the scenes. So what do I do? The same thing I did before. I create a weight matrix, WQ, that in a specific way so I can do a transformation. Just like before, we're doing a transformation, okay? So I'm going to transform X. I have the bias in here because this is what is also there, but we can kind of ignore it. That's the bias. And now I'm going to perform the matrix multiplication. So notice that the matrix multiplication is the original X, the actual data with the embeddings, with this weight matrix. These values have to be learned, remember? Now notice what will happen. It is still 32, so that means there's still 32 sentences, correct? And it is still 40, right? The 40 words, but I've changed the value to 64. In the past, all my transformations have been up, right? So I did 4 to 6, 6 to 12, whatever, but I can also do it down. That's, there's no reason why I can't do it down, right? So why did they do it down? They did it because they could have done it, kept it at 512, but when they do the attention, when they compare the sentence to itself, they actually said, you know what, let's think of this example as I'm going to give this to a human, and the human is going to think about this problem and give me an answer. Wouldn't it be better if we gave the same problem to 8 humans in parallel and then all 8 humans give us their answer. Do you see that? So they decided, okay, we're going to do the attention mechanism 8 times. But then they said, oh, well, that's 8 times, and each one of those at 512, that's going to be a lot of computation. Well, let's just compress it so we consume less memory and we can do 8 comparisons. So essentially, they decided that doing 1 attention at 512 was worse than doing 8 attentions at a scale of 64. Do you see that? Why can't they do that efficiently? Because they have a GPU. So the GPU can do that in parallel. So it can calculate the 8 attention heads all at once. And that's better than just 1 or doing it sequentially, right? So they were taking advantage of the GPU. And this is one of the best examples of how the transformer is built for the GPU. It exists because GPUs exist. So someone asked a question about quantum computers. So then there would be algorithms for the quantum computer. You know, there will be a quantum and it's for that. Just like the GPTs or LLMs, transformers, are built the way they are because of GPUs themselves. Yeah, go ahead.
In this case,
yes,
it's
transforming it, yes. And then, yeah. You're compressing the data a little bit. I agree. Well, that's what they decided. And because this is how it works. So the original transformer was called the encoder decoder with multi-head attention. Like it was in the name. And the multi-head meant this, 8 attentions. And so the sentence comes in, you know, the people were walking on the bank of the river and they decided that they wanted to do that comparison 8 times. So they do this. Okay, they say, okay, I'm going to take X, but I'm going to compress it to 64. Then I'm going to do that attention 8 times. Each one of those is size 64. And then we concatenate them. What is 64 times 8? 512. Do you see how they come back to 512? So they come back to that original size vector, but in parallel, they do 8 attentions. And each one you can assume could be different. They're independent. Well, they're independent. You just create another tensor. So you do, it's like you take the data, you compress it a little, then you do that same analysis 8 times, 8 results. I think I have a good answer here, a better answer. So I have 8. So what's one thing I could have done? I could have taken the 8 and averaged them. Do you see that? And so I could have kept it maybe at 512, averaged it somehow, but they decided, no, let's not average. Let's keep the exact answer for each one of the 8 and just make a tensor. Kept the information, and then it just keeps going. Remember that these are just operations with random weights. So during training, it'll learn the set of weights that works for that scenario. Do you see what I'm saying? Mm-hmm. Mm-hmm. Yeah, but it's think of it this way. So there's the 8 heads. It tried, you know, different set of weights for each. This result came out. It was not great. So what do? Try another set of weights. Now maybe these 2 get another set of weights and these 2 get another set of weights. Eventually, you're just giving it more. I'm going to try this and I'm going to try that and I'm going to try this. That's how I would describe it. It's like it's like when you roll dice, right? You want to get a 6. I didn't get a 6. But what if you can roll that 8 times? Are you more likely to get a 6? You are, right? So you can think of it that way. All right. All right. Great question. So now I have Q. Okay, we did that one. It's 32, 40, 64. I'm gonna add the bias, which you can see it's just another term that doesn't change the dimension. But remember that the bias is a learnable parameter, so it's love the weights. Okay, 32, 40, 64. This is like the line in high school, right? Slope times x plus b. And that's the y-intercept, right? It's the same idea. Okay, so, but now, guess what? I did q plus bq. Now x has been transformed to q. And all I did is 32, 40, 64. So I compressed it a little bit. And it's a vector space of 64 instead of 512 for each sample, for each word, actually. Now we repeat the exact same thing, actually, for K. I'm going to create my K. So this is the query and the other one is the key, right? But if you look, it's just X and a whole bunch of matrix multiplications. So now I do this one. Notice I create a weight matrix for K itself. Then I create the bias for it. Okay. Then I do the matrix multiplication yet again, because, so notice this matrix multiplication, same X, right? So the same set of sentences, but now times another weight matrix for K. And I compress it to 32, 40, 64. Do you guys see that? All right. Now we add the bias. Okay, 32, 40, 64. But now I have my Q and my K, which is still my X, and I'm going to now compare them. All right. That's where this comes in. Attention, which is going to be Q, matrix multiplication K, and this will produce a matrix that is n, 40, 40, which means that now you can assume all the tokens are being compared to themselves, because those are the sequences. So I'm going to do this one here. So notice torch map mole of Q and K. This transpose is just to make sure things align correctly. I think we did an example of that the first week with tensor operations. I just made the thing like that, right? So that's what a transpose is. But Q comma K and boom, 40 by 40. Why 40 by 40? Because, if you have 40 words here, you want to compare it to the 40 words over here. Do you see that, guys? So we've arrived. This is actually the attention right here. So now let's think intuitively, right? What's happening? So I'm going to switch to the whiteboard. Okay. So notice here, I've created, pen is not working. Oh, there it is. Right. So I've created this matrix by doing a matrix multiplication Q, K. But essentially these are X and X. So this is 40 and 40. It's squared, right? And so the example was the bank of the river of the rivers. You can think of it as still the bank of the river, but transformed. Now, this matrix multiplication still just gives you random weights, right? But imagine that you have now the LLM. Text comes in here, right? And you want to understand something about it over here, right? So somewhere in there, you have this attention mechanism. Somewhere in the network. There's actually many, right? Many attention mechanisms. So you want to understand that you read this sentence, the bank of the river, and the transformer wants to know what this bank means, right? So what's going to happen is it's going to try multiple types of weights until it finds one that correlates these two things. And it's probably going to say, in a scale from 0 to 1, that this is like a 0.85. You see that? It's going to learn that weight. And what does that mean? It means that in this context, river and bank have a high correlation. So now I know what this means. It means that type of bank, a sandy area. Do you guys see that? So that's essentially the idea. So the bank of the river, no, the bank of the Cache River. Okay, so now in the context of, we're still looking at bank. We know that there is a bank that's related to cash, right, where there's money in a bank. But in this particular case, the neural network is going to say 0.05. This bank is not about the financial institution. This bank is about the river. This is how it's able to solve that really hard problem, actually. Do you guys see that? So this is the intuition of the attention mechanism. It learns to pay attention to the words around it to figure out what everything means. Instead of there being just, there's a vector. So you can think of it also like there's two vectors. So there's a bank and bank, right? So bank for river. So river and bank for cache, right? So they're both vectors of size 512. But they're going to have different values depending on the context. That's the magic of the transformer. Do you guys see that? That's essentially what the attention mechanism is doing. And that's how it's able to differentiate one from the other. Okay? So because all of this is embedded in the neural network itself. Okay, so, but it again, these are weights in the matrix, right, that have to be learned. That's why it needs all the text in the world to be able to learn these attention weights and all of that to do these transformations. Okay, so now you can think of it as this sentence comes in, it gets multiplied by a set of weights, and boom, 0.05 and 0.085 emerge. I know exactly what type of bank I'm talking about. Okay, so now let's if the thing was inverted, maybe this would be 0.90, and then this one would be 0.05, and guess what? It knows that it's talking about the financial institution right away, just by that. All right, so that's the attention mechanism. So let's finish it up now. So we had a matrix that is, because this is kind of nice, so 32, 45, right? But I already told you guys that everything that comes out of an attention layer or a block in the transformer needs to be back to 32, 40, 512, right? It needs to be back to that. So that's where the other term, the V, comes in. So we're going to use this V to change it back to what it was. So what is this one? Notice I create the weight matrix for V. There it is. And I'm going to create its corresponding bias for V. There it is. And then it should be the matrix multiplication. Oh, here, just to create V. So what is this one? Once again, X, right? I take the X's originally. the weight matrix and produce my new V. Just like I created Q and K. I create V now. I add the bias. And now my V is ready. And remember, my attention was here, right? In attention scores, but it is a 32 by 40 by 40. I'm going to multiply this attention scores, matrix multiplied with V, to produce my original tensor 32, 40, 64. So that should be this one. Okay, notice torch map mole, the attentions matrix multiplied with V. Do you guys see that? And boom, 32, 40, 64. We're done. I just did one head of the 8 parallel heads. Again, it's just like instead of giving just you the problem, I took 8 of you and gave you the same problem. In 30 minutes, you all did it. And then now you return the answers, and I have 8 answers. So what do I do with it? I could have averaged it, but they decided no. Sorry? And they decided not to average it, but to concatenate it instead. And that's how it is in the code. All right, so let's take a look at that. So I have one head complete. Now notice here I wrote concatenate all 8 heads. So I have kind of created like a simplified version of this in the code. You will see how it's done exactly. But notice what I'm doing is pretty close to the reality. So what I do is this. Out is essentially the result of taking the x's, converting them into K and Q, matrix multiply K and Q to create the attention scores, and then that multiplied with V, and I get head, out, right? 1. Now, I just create a little list, and I'm going to iterate from I to 8, and essentially I just populate it with the same tensor 8 times. And that simulates the 8 heads that I would get in parallel. So I do this. So this allows me to concatenate something. So now if you look, if I iterate through that list, I have 8 tensors in there. You see that, guys? I have 8 tensors that are 32 by 40 by 64. And that essentially is the 8 attention heads that I calculated in parallel. And now I concatenate them, and I will get my 32, 45, 12 again. And I'm back to where I started, but I've done all these transformations. I paid attention and all of that. So that's what I'm going to do here. There it is. So notice, oh, I just did this. Sorry. This is the... So I just printed this. Now I'm going to do the concatenation. Do you see that? So I take list head, which is the list of the 8 attention heads. I use torch concat on the last dimension. Remember, -1 just means the last, and boom, 32, 40, 512. They're in there. Any questions on this? Again, this, these operations are currently broken up, right? But once we start looking at the whole flow of the code, you'll see where everything is, and what's happening essentially behind the scenes. Any questions? Yeah, go ahead, please. It's a good question for both. So it's in it. So all of this is in the network. None of this is outside of the network. So when you create the network, right, you train it, but this is embedded in the architecture. And then when when you're done with training, the only difference is now you have weights. You have a nice set of weights. Now you're going to use it for inference. The attention is there with the weight so that when you give it new text, it runs through all of this. And the key thing, as I said, is it's when you get the bank of the river or the bank of the Cache River, as I said, it's gonna light up bank and river as being connected and not bank and cache. So it knows what you're talking about. Yes? Mhm. Mhm. You could. That's how neural networks in PyTorch work like that. So the n value is like undefined. So that value could be 32 or it could be 1. So it works perfectly. So because during training, you want to train in batches. But as you said, when you're done with inference, you don't need to give it 32. You just give it 1, right? The question that you're asking. But it still works perfectly fine. You could, no, it would be like you're asking 32 questions because you can actually, imagine you're a company. You start your own startup, right? And you have a GPU in the cloud. You're going to have 32 people all over the world paying and asking you the question, their own question. So what do? You could give it all 32 questions all at once and get 32 answers, and then you just send it to all of them. You see that? So that's actually also possible. You don't have to do just one. So in training, you can give it batch, but also in inference, you can give it batches, or you can just give it one. Any other questions, guys? Is this making sense? So these are the essential operations, right? And believe it or not, these are like the hard parts. The only last hard part that's left is the mask. That one's a little bit tricky, and I'm saving it for next week. But yeah, so this is fundamental. So you've seen the common theme today has been the dot product, then the matrix multiplication. We did it pretty simply with iris, and then I extended it to attention mechanism, which is text. But essentially, the underlying is still the same. Okay? Vector spaces. All right, so let's see where we are. So we have done this one over here, and we have arrived at 32, 45, 12. So essentially, it's like we went into a block and just came out. And now we could go into another block and do the same. In fact, notice over here that you can actually do another projection just because, and this happens in the neural network. So notice here, I have another weight matrix, W0, with some value here, a bias, and then I matrix multiply it with what I just concatenated, right? And that's just another transformation. I could do that if I wanted to. Do you guys see that? And this is more of a feed forward normal neural network projection, not an attention projection. This happens in the transformer. I think they just said, let's just try one more feed forward to see what, if that, for some reason, but it's in there. So we can try this one if you guys would like. So I'm going to do W0 and we can play with it. So so remember, I have what just came out of the whole attention block, this one, right? Let's call it out_cat. Remember that has concatenated the 8 heads, right? And now I'm just going to do yet another projection. I'm going to use obviously a different name, W0, and it's going to be N, by 8 times 64, which is 512. And then I can make this actually 2048, just for fun. All right, so I'm going to do that. That's W0. Then I need a bias, of course. So 2048. And now notice I'm going to do yet another matrix multiplication of the concatenated 8 heads, right, which is n by 40 by 512 times this W0. And notice what I just did. It was 32, 40, 512, and I transformed it into 32, 40, 20, 48. Why did I do that? Why did they do it? I don't know, but it's in the paper, right? Think of it as adding it another layer to think a little bit more. Because what's hilarious about this operation is then they just make another one to bring it back to 30 by 40 by 512. Do you see that? So I'm not kidding. That is in there. So imagine I just do this exact same thing again, and it just brings it back to 32, 40, 512. They consistently always, as I said, maintain that tensor throughout, but they have layers where it goes up and then down. And those weights have to be learned, and maybe the intuition is that you have to give it more room to think. Okay? All right, so we've done that. That one, I think by this point, you guys can do on your own. All right. So I think I only have like a couple of things left. As you can see, the mask is one thing we need to discuss. That requires like, us to start fresh with this one. So that'll be next week. Okay. I'll leave the mask for later. Because it's, as you can see, quite extensive. So we'll cover this one next week. But I want to cover this one right now. Token embeddings, and positional encoding. So this part of the thing is actually at the very beginning of the GPT, right? So it's almost going from string to integers and so on. So let's talk about this one. So token embeddings. So I'm going to copy this. And then you guys are saying, but you promised that you were going to show us a baby GPT, and it's almost the end of class and we haven't seen anything. Well, this is kind of like, did you guys have seen this movie, Karate Kid, right? So I've been having you wax on, wax off, paint the fence, sand the floor, right? And at some point you might question, but you didn't teach us karate at all. But you can sand the floor, paint the fence. So you'll be able to then, that's where you put it together. Anyway, it's a bad joke. But anyway, all right. So yeah, so that's kind of what we're doing, right? So let's do the token embedding, right? So how does that work? Because I only drew that in the whiteboard. Now you're going to see it in the code, how that works. So I have a vocabulary size. Instead of 50,000, let's assume we only have 1,000, just to keep it simpler. And remember, again, I'm still just assuming words, although that's not the correct thing. Notice the embedding size is 512. Sequence length, just to keep it, I want to be able to visualize this a little bit better, and 40 is too long to actually notice. So 10 is a little bit better, and just 2 sentences instead of 32, right? So the goal is to visualize this a little bit more. So there we are. Now I'm going to create some random data. So this is just some random integers to show you what this looks like. So I'm going to do tokens. Right, so I create that string tokens. Then I'm going to do tokens.shape. So it is 2 comma 10. What does that mean? 2 sentences of length 10. Got it? All right. So now visualize it. So tokens. And that's essentially what it looks like, okay? Only these are random values. But you would have a batch of 2 with a list of IDs, where each one of those IDs means cat, dog, whatever it is, okay? So now this is what you give to the neural network. We'll do this later. So you give it a tensor of 32 comma 40 or 2 comma 10. That's you. That's on you to do. That's like the starting point of the neural net, right? And then the neural net now starts to do its thing in the architecture. So what we need to do now is obviously do the embedding. So this is the actual PyTorch code that you will use to do that. PyTorch has this, and also TensorFlow, they have this construct called the embedding layer. The embedding layer is just like a neural network layer, but the goal of it is essentially to take IDs and map them into their embedding space. Okay, if you notice, it's called NN embedding. It says the number of embeddings, vocab size, so 1,000. And then the embedding dimension is 512. So it's that matrix of 1,000 by 512 or 50,000 by 512. Okay? So you create that there. Oh, and then it's not defined. So let me grab that. Okay. So there we are. I've created the embedding, and now it's just a layer. So I can just give it data. Notice here, I'm going to take the tokens and I'm going to run them through the embedding layer. So you see tokens 2 by 10 goes into embedding, and guess what? It comes out as 2 comma 10 comma 512. Does that make sense, guys? Any questions about this? This is how I took the 2 comma 10, 2 sentences with a list of IDs, this thing here, right? And I ran it through the embedding layer, so it becomes 2 comma 10, 512. Now, each of those IDs is represented as a vector of 512. Make sense? It'd be difficult to see, but you can grab one and look at it. It's just going to be random values, and 512 of them. Any questions on this? All right, great. So this is the embedding. So at this point, you're in the neural network. You're in the transformer, okay? And the transformer needs to learn these values. So currently, these values are random, but during training, it'll learn the actual ones because it's, guess what? Another matrix multiplication of weights and inputs, okay? So I've done this one. That one's pretty intuitive. Now we're going to cover positional encoding. Believe it or not, for some reason, it took me years to understand positional encoding. It's simple, but I think it was just so simple that I couldn't believe, because there's the mechanics and then believing that actually that works, but it does. So what is positional encoding? Positional encoding is this idea that it matters. And we'll wrap up probably with this. So what do I mean by that? All right, so let's consider the following sentence. The car is going fast. Do you guys see that? Right? That has some meaning. What if I write the fast car is going different meaning, right? I could say going slow, but not, to keep this, to use the same words. And the only thing that changed here is honestly the position of the word fast, right? And when I imply maybe it's like a Ferrari or something, but it's just going really slowly, this could be an old car and it's going really fast, right? So the position matters. So when just like we have embedding for each word, we also want to keep track of what, is it at the beginning? Think of it this way. Is it at the beginning of the sentence, the middle of the sentence, the end of the sentence? So the sequence, where is it? We want to keep track of that. And so how do we do that? Because the problem is, there used to be this thing called RNNs. I mean, it still exists, but it used to be the tool to use before GPTs and transformers. And that was a sequential thing where you would literally have a network where the first thing was then that went into first, then that went into car, in sequence like that. But the problem with that is that you couldn't process an RNN in parallel. Why? Because since one needs to go into the next one, you need to process fast first, and the result of that will go into car. And so you can see that that is too slow. In parallel, you can just send everything into the GPU. So that you needed another approach, and they invented this thing called a positional encoding. Okay, so let's see how that works. It's a little bit like you just, how this was 17 and this was 5 and this is 60 and this might be 3 and 40, right? For the token embedding. For positional encoding, all you do is you mark the position. 1, 2, 3, 4, 5. So you have two embedding matrices. One for like the semantic content, this one, and one for the position. Okay? So now think of it as two of those NN embeddings. You have this one and you have this one. In the positional and in the normal embedding, it goes from 1 to, let's say, what was it? 1,000 words. Right? And we figure out a 512 embedding. Do you guys see that? In the positional embedding, it goes, what is the length of our sentences? 10, right? So it goes from 1 to 10. And this is still 512. So every word will have this embedding that means semantics plus another 512 embedding that just means position. But it has to be learned by the neural network. See, it's simple, and yet, because you want to add it to the
Yeah, essentially.
yeah, for the math to work later. Yeah, yes, exactly. So essentially, you're going to do this. X is the sum of two matrices that are the exact same size, but one holds like semantic embedding information, and the other one holds positional embedding information. And they need to be the same size so you can add them into just one tensor that you always want to be 32 by 40 by 512, or whatever you've decided the right dimensions are. But the beauty of this is, just like this one is just random weights that must be learned, this one is random weights that must be learned. So it's like you're letting the neural network figure out what the right embedding should be. Do you guys see that? And since you know that this is a fixed number like 40, you can do it. So we'll see that in a second. We have like 12 minutes. 12 minutes. So let's now do it. So I'm going to do that concept. Took me a while to understand. There's another approach, which is sine and cosines, but I'm skipping that right now. I'm sticking with this one. Okay. So let's do, so now positional and token embedding together. All right. So I'm going to repeat this process. I think I changed the values here a little. So notice here, vocab size 1,000. I changed the embedding size to 64 instead of 512. That's the only difference. Okay, you later can try it. Still, the sequence is 10 and the batch size is 2. Okay. All right, so now I'm going to create the tokens sort of randomly for now. See that? That's just the IDs, right? The cat is sleeping, converted into integers. All right. Now I'm going to do two embedding layers. Notice this, right? With the exact same construct in PyTorch, the nn.embedding. So notice when I'm labeling token embedding and I'm saying it is vocab size, right? The number of words, 10,000, 1,000, or 50,000, and the embedding size, which is 64 for my selection here. Do you guys see that? All right. So I run that one that just created that layer. And now I'm going to create a second layer for positional encoding. Okay, notice this one, different name, positional embedding, still the same construct and then embedding. Number of embeddings is now not vocab size, but sequence length, 10. Or if I was in the paper, 40. Okay, and embedding size the same as here, 564. Because as you said, it's just a convenience that they need to add up together. All right, so I do this now. There we are. Both of them are done. We know the shape of tokens is 2, 10, so I'm going to skip that. And now I'm going to run the tokens through the layer. So notice first the token embedding, kind of the semantic meaning. I run tokens through it, this one. And now it is 2, 10, 64, right? I've done that. Now I'm going to do the positional embedding. This is probably what took me a long time to comprehend. Initially, when I was doing the positional embedding, my brain just couldn't understand, but I should run the X through this. I should run X through this to get the positional embedding. But if you notice, we don't run X through it. Notice that I'm going to use torch A range with sequence, and I'm just going to create a tensor. Whoops. Do you see that? I'm not actually running X through this layer. Instead, I'm running a tensor of 10 where the indices are just 0, 1, 2, 3, 4, 5. What are they saying? They're just telling you that this word is somewhere in the beginning of a sentence. This word is somewhere in the middle of the sentence. This word is somewhere in the end of the sentence. That's essentially all that it's capturing. But I don't know if for you guys, intuitively, I would have thought X has to run through it because X always runs through everything, but not in this case. In this case, and this is a trick, like this was brilliant. And so now that this is done, the position is like this. So notice over here what I do is I use the positional embedding, but what goes into it is positions and not X itself. So I run it here, and guess what the shape is? 2, 10 for the original one, the normal embedding, and 2, 10 for the positional encoding. So essentially 2 tensors of the same dimensions that I can easily add together. And that's literally what they do next. You can see that right here. So token and the X token, which is what comes out here, and the X position, they just get added together. And if you look at the shape, it is 2, 10, 64. Does that make sense, guys? So remember, this is just the operation. Weights are there every time that are the thing that will be learned to produce the right result. Make sense? So in the few minutes, so that actually takes us to the end, right? So we got to the end of this. What's left for next week is we're gonna hit the mask. But what I want to do now in the last 5 minutes is now let's go to the actual code, right? The actual proper LLM, not even the baby GPT. We can do that next week. But let's take a look at, let's go back to the repo. Okay, so how LLMs work. So for your homework assignment, remember the code that you will be using is this one, GPT Scratch Huck Finn. All right. So there's still quite a bit we need to cover, but I just want to show you that a lot of the things, the wax on, wax off thing, where does it fit in the actual code? So this is the code, right? You can see, you start at 40, right? You define the parameters 40, embedding 512, right? So now these values start to make sense to you. Let's look, all we're talking about is the architecture here, and here's the architecture. So notice this one called class head. You guys see this now, right? And it should start to look familiar. This is what? The attention layer. Do you guys see that? What's happening here? You have a K, a Q, X goes into it, correct? You guys agree that X goes into it, gets modified? And then what happens to K and Q? They get matrix multiplied to produce this matrix over here. Do you see that? And then that one over here, guess what? X goes into value to produce V. And then you take that one, matrix multiplies with V to produce out. Do you see how that's pretty much what we just did? Except that my version was a little bit more simplified, right? This is like the actual complete code. But you can see the elements of it. So that's just, the attention mechanism. Here's the feed forward where I took the matrix from 512 to 2048 and then from 2048 back to 512. Just that happens. Here's the multi-head attention. Remember how I had 8 heads? There's the list of heads. What do you think is happening in this function here? The concatenation. I'm taking the 8 heads that I'm going to create and just concatenate them together. That's that idea. This is just a projection. Notice this is a block where you build essentially the whole architecture. So you have a multi-head attention. That comes out. So it's X goes into like a normalization layer. Then it goes into this multi-head attention. Notice there's an X plus that. So we need to talk about that. Those are called residuals. That's something very, very important. Then this X goes into another normalization and a feed forward layer. Now, this is the whole GPT model. So if you look, does this look familiar? And an embedding, that's the semantic embedding. What about this embedding over here? That's the positional embedding, what we just talked about. So now look over here. IDX is my X that I was just, the initial tensor. IDX goes into token embedding. IDX does not go into positional embedding, right? But now you have token embedding and positional embedding, and what do? You add them together. Do you see that? And then that goes into all the blocks that have all the attention layers. So essentially, and that's it. That's the full code for the GPT. We have looked at individual pieces of it, right? But we obviously still have a few things left. But I wanted to show you all the things that I've discussed, where they start to fit in the final code. Does that make sense, guys? All right, so next week, what I recommend is don't look at this code yet. Don't look at this code yet, but instead look at the baby transformer, okay, which is this one, baby transformer. Look at that one because that's a simplified version of everything we've done. Do you see that? Try to understand that one first and specifically the flow of it. And then from there, I'll pick up here next week. So next week, I'll plan to cover this masks also. Just keep going until we've done everything. And then we'll do one where we go through the entire Huck Finn GPT. All right. So it's 9:20. So we'll stop here for today.